Okay, so last lecture, what we did was we just, very, very intuitively described what we're going to do in class. Like I described sort of some of the applications of complex analysis and so on, and the intuition and the main results and why they're important. Very, very, very high level, very superficially. So now we'll start with actual material. And basically we'll follow all first. So the reference that was on Moodle and on the forum and so on. And we'll follow this quite closely until maybe section like 5.1 including. And so this is like the first one with around 200 pages. And then I'm hoping that this will give me maybe like 2 weeks in the end, somewhere between 1 week and 3 weeks, where we have a bit of freedom to explore other things, right? And then we can even decide altogether what it is that which branch we go, because then there's many good options for what to look into. Okay, so let's start with basically high school revision. Right, so just basic properties of a complex number. So we'll go through this rather quickly, and then we'll start speeding up, and maybe by next week you'll start seeing new stuff. Okay, so the complex numbers are. Okay, so we defined the idea of complex numbers was to have both R and sort of introduce and add a number I, which we think of square root of 1, right? Such that I squared is equal to -1. I is like the square root of -1, but you want to keep all the properties, right? That the nice properties that the real numbers had. You want to be able to add things, to subtract, to multiply, to divide, and so on and so forth. And so actually what we need is we need the whole, right? We need all linear combinations of reals and multiples of I. Right, so the complex numbers are simply all pairs of numbers alpha, I, beta, such that both alpha and beta are equals. So we take real numbers, what we call purely imaginary numbers, so just a multiple times I, right? To square will be a negative number, right? It will be like minus beta squared. But then we also take all possible linear combinations of this, right? And you might already think this looks an awful lot like R2, right? If you go back to linear algebra, this looks a lot like R2. And in fact, a lot of what we're going to do today, you could view this as simply R2, right? The nice thing is that you can define nice multiplication here. It makes sense to multiply these numbers, when in R2 you have to be a lot more careful about that. Right, so how do we add? How do we add two complex numbers? Well, I have two complex numbers, alpha and beta plus. Right, then I can think of it as elements in the vector space. Like in R2, I just add exactly like in R2. Right, so I just have the real parts and I have the complex parts. Right? So we're starting really, really at the beginning. Right, now what's maybe a little less obvious is multiplication. So how do I multiply two complex numbers? Right, if they were elements of R2, multiplying one can mean different things, right? There's the inner product, the outer product, and right, neither of them feel like a real multiplication in the sense of, two numbers giving a number, or two elements of the same space giving one again. But here we can multiply them, right, in a way that's sort of much, much more natural. Right, and so what is the product of the two complex numbers? We can just use, the normal rules that we would like to be satisfied when we have, numbers, like things should be associative, they should satisfy the distributivity property, and in particular, they should be commutative. I mean, not always things are commutative, as you know from linear algebra, but it will be the case that things are here. Right, so we can just use the distributivity property and take this as alpha, right, plus gamma, plus alpha delta I, right, plus, I should be a bit more consistent. Let me put the I before. I mean, it doesn't really matter at all, but just for the sake of consistency, right? So then I alpha delta, and then I have I beta gamma plus, right? I get I square, which is -1, and then I get beta. I get beta delta. Okay. Now the only thing I used here was distributivity, right, and the fact that the product of these numbers commute. Okay, so what is this? I collect the terms that have no I. Right, so I get alpha gamma minus beta delta. And then I collect the terms that have I plus I delta. Okay, so this feels, the first time you see it, maybe like a strange way to define multiplication, right? But this is the way that will give us, one would have to check that everything is consistent and so on. But this, right, just using the properties that we would like to hold and just carrying out distributivity, you get exactly this, and this will be our multiplication for complex numbers. Okay. It's worth noting maybe that, commutativity here is kind of clear, right? Because you have this new number I, but we know how to make sense of powers of I because I squared should be -1, right? And when you multiply, it's kind of clear that everything is commutative. But there are other there are other sets of numbers like the quaternions, which you might have heard of, in which you don't only have an I, but maybe you have an I and the J and the K, which are special numbers. And then it's not quite clear anymore that they're commutative. And in fact, in some of those cases, they're not, because it could be that, when you define the product between these new numbers, that defining, say, ij and ji could be different, right? But here it's not the case, right? I times the real or a real times I is exactly the same, and so, of course, everything will be commutative. Okay, so what about division? Okay, so we know how to add. We, of course, also know how to subtract, right? We just add the symmetric. How do we do division? Right, so it's enough, of course, right, if we have a number alpha I beta, right? It's of course enough to be able to define 1 over alpha plus I beta. Right? If we know how to define 1 over alpha plus I beta, then we can just multiply by that. Okay, so let's say we have alpha plus I beta, right? It better be not 0. Like, we're never allowed to divide by 0. It doesn't matter where we are. Right, so how do I make sense of 1 over alpha plus I beta? It's not clear a priori that I can divide, right? I mean, think about, a vector space R2. What does it even mean to divide, to divide a vector by another vector, right? This doesn't a priori make any sense, right? But here we would like to be able to divide. Right, and so how are we going to make sense of this? Well, okay. we just write an equation, right? What we would like the numbers to satisfy is we would like alpha plus I beta, right? And now we would like for there to be a complex number, x plus iy, and for this to be 1. Right, and now we just have to try to understand whether we can solve for x and y. Right, but now this is relatively easy, right? Because what does this mean? This means that ax, right, plus this times this, which is minus beta y, needs to be 1. And, right, the part with I needs to be 0, because this number doesn't have an imaginary part. Right, so bx plus alpha y needs to be 0. Okay, so now we have a linear system of 2 equations and 2 variables, so that's looking good. Usually they have 1 and 1 solution. Right, we can write this as a matrix. Right, so what goes there? We have alpha minus beta, then beta plus alpha. Right? The solution to the quotient, the inverse of alpha plus I beta is just a solution to this. Right? So will exist. Right? If as long as the determinant of this matrix is non-zero, then yeah, the solution will exist. Right? So we just have to take the determinant of that matrix. Luckily, this is a nice matrix to take the determinant of. Right? As long as this is non-zero, we're okay. Right? This is what we learned in linear algebra. Right? But what is the determinant of this? This is just this times this minus this times this. So we get. But this is equal to alpha squared plus beta squared. And now remember, these numbers are real, right? So the only way the alpha squared plus beta squared is 0 is if they're both equal to 0. But this can't be true, right? So this is true because, right, and it's non-zero because alpha plus I beta is not 0, right? We're never allowed to divide by 0, and here the same. Okay, since this is not 0, then indeed there is a solution, we just have to find it. Right, but now instead of solving the linear system, we can actually find it, not a lot more neatly. Right, let's say we have something like this. Right, we want to write this number. Right, so I'm going to do a trick that you'll do many, many times. Right, it's like the complete the squares kind of trick, right, which is you multiply here by alpha minus I beta in both sides. Right, so what do we get? We get alpha minus I beta. And here, right, what do we get here? We get alpha squared. Right? Now let's look at the other term without an I. It's I beta times minus I beta. So it's minus I squared, which is 1, so you get beta squared. So you get alpha squared plus beta squared. And then what happens with the terms in I? You get, I should of course keep this like this, right? I get alpha minus I alpha beta plus alpha I beta, right? Just x minus y times x plus y is x squared minus y squared. And so now this is already in the nice form that we would like. Okay, minus okay, I sometimes put the I before the number and sometimes after. There's no real reason for one or the other. Okay, so indeed we can divide, right? As long as the number is not 0, we can divide, and the result is simply this new number. And now, of course, if I want to take a number divided by another, I can just multiply by the inverse. Okay, so this is alpha. Okay, so we know how to divide. That's good. Okay, now let's do something a little more interesting. Let's try to take a square root. Okay, is there any questions so far? If there's any questions, please interrupt. Okay, so now let's take a square root. Okay, so in a way, I mean, this was the whole point of the complex numbers, was that we could take square roots of things we couldn't take before, right? We sort of created this so that we could take square roots of -1. So now let's see that we can actually take square roots of all the numbers, right? Or if we just introduced other numbers that now we can't take the square root of, so we need to create a new number and then have that create more and so on, and we could go in some sort of, right? We could go ad infinitum just creating more and more numbers, right? But I already told you earlier this week that this wasn't the case. Then any algebraic equation will have actually a solution, right? It's sort of the power, one of the main properties of the complex numbers, and so in particular, everything will have a square root. Right? Because the square root is just a solution to the equation x squared minus the thing you want to take the square root of equals 0. Right? But let's try to actually compute and see what it is. Okay? So let's say that I have a number, right? And I want to think about what's the square root of alpha plus I beta. So in particular, I'm looking for a solution. And then there's going to be some calculations, but there is a valuable story that will appear as we do these calculations, and so it's worth doing them all together. Okay, so how do I solve an equation like this? Well, for now, the complex numbers for us are nothing else than just pairs of reals with some strange rule for multiplication. So let's just write an equation of the reals. Right? So we get that x squared minus y squared, right, will equal to alpha. Right? It's just matching the real parts of these numbers. And 2xy will be equal to beta. Right? Okay, so now let's do some algebraic manipulations. Right? If I take the square of this, I get something like x squared y squared, which I know how to make sense of. I have like x squared minus y squared, right? So I can easily also make, if I have, say, x squared minus y squared squared, I start getting things like x's and y's and powers of this that I can control. So that's the idea, right? So we're just going to write, x squared plus y squared. Right, we'll write the square of this, and stuff like this starts to show up, and then this will allow us to solve for x and y. Right, I mean, trick. Okay, so in particular, Okay, so if I compare, well, plus something, of course, and that's not done. Right? If I compare what this expression, how it compares with this one, right? I get like an x to the 4, I get an x to the 4 here, I get a y to the 4, a y to the 4 here. The place where they're not the same is in the cross term, right? The cross term here is positive and here is negative, right? I get like 2x squared y squared, and here I get minus 2xy squared, right? So I have to compensate by giving it twice the cross term, right? Is this clear to everyone? Okay. So now I already start having, start being able to make sense out of all of this, because now what is this? This is just alpha squared plus a beta squared, right? This is exactly alpha squared. This is exactly beta squared, right? So in particular, we have, what is x squared and y squared? Right? I know what their difference is, right? And I also know what its sum is, right? Okay, so maybe let me do this. I don't do too many steps at the same time. This means in particular that x plus y squared, right, is equal to the square root right? Because all these numbers are real, all this stuff is positive. So it is the square root that we know and love of, like a positive number is just a square root that we're familiar with. Okay. And on the other hand, x squared minus y squared is equal to alpha. Right. And so, now these equations are extremely easy to solve. Right? To get x, we just need to add, if we add both these things, we get 2x squared, the y cancels out. So the value of x squared is just half of the sum of these things. And for y squared, we just have to take this one minus this one, right? The x cancels out. And the y, you get 2y squared, so it's just half of that. Right? It's this minus this, so minus alpha plus okay. Let's see. Maybe I'll try to go here. Okay, so what does this mean? This means that I can have x be plus or minus right? Okay, important to notice too, right? I have y squared, both y squared and x squared are equal to this to be positive, right? But it's not so hard to tell that, alpha and minus alpha, even if they're negatives, when you add this, they'll always be positive, right? Because here, if beta was 0, right, then you would get, right? You would get the absolute value of alpha, right? So it always beats either alpha minus alpha to be positive, and when beta is not 0, it's just going to increase it, right? So this is okay. These numbers are always bigger or equal than 0, right? They may be 0 when beta is 0, but if beta is not 0, they're certainly even bigger than 0 always. Okay, so we get this. And plus or minus. Okay. So what are so how many possible values for the square root do we have? At least what does it look like? Okay, so it looks, right? It looks like we have 4 possible values. which is a very strange, thank you. I just saw someone wrote, of course, there is, of course there is a square root here. And a square root there, thank you. Okay, but now it looks like we have 4 different values, right? Because this can be plus or minus, this can be plus or minus. We're when you take the real numbers, you take the square root of 4. I mean, we always say the square root of 4 is 2, because we decided that we would take the positive number, but minus 2 would also solve this equation, right? Minus 2 squared is also 4. And so even though we've defined the square root over the reals to be just a positive number, we can in some way think that there's 2 square roots, but certainly not 4. Right? And in fact, the square root, right, this equation is equation of degree 2, we should not have 4 solutions. Right, so what's the problem here? Take 10 seconds, 20 seconds to think about this. Exactly, right, so someone wrote in the chat, we have this equation, right? These derivations are not equivalent, right? These were just one-way implications, and in particular, we have this equation here. Right, so if beta is not 0, right, then the sign of x times y, right, needs to be the sign, right? By sign, I just mean being positive or negative, right? Needs to be the sign of beta. Right, and these are all positive numbers, so if beta is positive and I pick a plus here, I need to also pick a plus there. If I pick a minus here, I also need to pick a minus there. And if beta is negative, it's the other way around. Right? So this makes it so that if beta is different than 0, then actually there's only 2 possible solutions. Okay, and I'll write them down what they are in a second. But let's first intuitively think about this again a little bit. So what happens if beta is 0? What's the catch if beta is 0? Right, then either x or y are 0. There's 2 ways of viewing this. One way of viewing this is by this definition, right? If beta is 0, then either alpha plus its absolute value or minus alpha plus its absolute value, one of them is 0, right? Because all this stuff is right? Here these numbers are all real. Or another way of viewing this is this equation. Right? If beta is if beta is 0, then either x or y are 0. Right? And so really, one of them is 0, and so this right, the choice that we thought we had, and we didn't really, right? Because plus or minus is just the same. And so, right, and so if it is 0, then the number is either real, so either x equals 0 or y equals 0. Okay, let's look back at what this means. So okay, so let's think a little bit about this. So if beta is 0, then what I'm saying is that either x or y are 0. Right? So the number is either real or purely imaginary. But let's see about when does that happen. Right? So it's not hard to see that basically, I mean, we can think about it in what happens in these equations, or we can think about it in what happens from what we know from these numbers, right? If alpha is positive, right, then the square root should be a real number, because these are numbers that we've always known to take square roots of, right? And so then y is going to be 0, and you're just going to have x as a non-zero, right? And if you work out those equations, we'll give you the same. On the other hand, if alpha is negative, then these are exactly the reason why we created the complex numbers, and then x is going to be 0, and the number is going to be purely imaginary, right? And if you work out what these equations give you, they'll give you exactly the same thing. Okay, so let me just write the solution. Now, you just have to be careful about the sign, so I'll just write it out. Let me erase the board first. There was something else actually that I completely forgot to say on the logistics side, which came up last time, and it's a good point, which is that if you, for some reason you would like to ask a question in a private way, that your name doesn't show up, on the chat, you can ask it privately to the assistant that I have in the room and handling the questions, which today is Viola. Can you just write something on the chat? Just hi, or so if you ask privately to her, then she can just read the question, right? Okay. All right. So let me write out what the solution is, right? So right, there's a point to this. We'll see. I mean, it's exactly what I wrote before. There's nothing mysterious about it. The only thing is that now you have to pick the same sign, right? If you go plus here, you need to go plus there. So maybe actually I should move the plus or minus up here to make more clear that that's the case, right? But right, you weren't always going to pick the same size. You were going to pick the same size depending on the sign of depending on the sign of beta. So this is just here to tell you what the sign of beta is, right? So that you pick the same if it's positive and you pick different if it's negative. Exactly the same thing. It doesn't really matter what these expressions are. The point I want to make, I'll make in a second, but just to make it more concrete, let me have them up. Yeah, okay. And then if beta, right, of course, if beta is 0, there's trouble, as we saw before, and in particular, right, you're dividing by 0 here, which is, of course, a bad idea. And then in that case, we already said, right, we already saw this, if alpha is, say, bigger or equal than 0, then x is equal to plus or minus alpha, right, and y is 0, right? And if alpha is negative, then x is 0, and y is equal to plus or minus square root of minus alpha. Okay, so now the point I want to make is that this seems to have two options, right? It's not quite clear how to define square root, right? Over the first time you learned about square root, you may have wondered, or maybe not the first time, but at some point, you may have wondered, why isn't the square root of 4, minus 2 rather than 2? And we just, because it's sort of clear that, defining it as 2 rather than minus 2 makes our life easier, we just define it to be the positive option, right? When we take the square root of a positive number, we have two options, and we just pick the positive one as the right option, right? But here, it's not clear what the right option is. Someone asked a question, isn't it? Someone asked if this needs to be real. Yes, because in this case, alpha is negative, right? So then this is positive, and then this is well-defined. Okay. But so the point is that here, it's not clear at all that one, picking the plus or minus here, that one makes more sense than the other. Right? It's not a priori, clear at all. And so in particular, many times the right way to think about the square root is actually as, both these values are the square root, and we can just think of it as a function that has two branches in some way. Right? And while for the square root, this doesn't seem like to be such a big deal, because over the reals we're able to fix it by just picking one and so on. Turns out that this issue, that some functions we'll want to define over complex numbers have multiple options. It turns out that this is a core issue in complex analysis, and actually will be a rich one that will give us, not only cause problems, but actually give us be the reason why some of the theory actually works. In particular, the different branches of the logarithm function are going to be very important, right? When we take the the inverse of the exponential, right, over the reals, this is not a problem, right? It's completely injective. But I already hinted at last time that waves and cosines and sines and things like this, that these will be right. That these will also be matrix. They will also be exponentials. Just exponentials where the argument is the imaginary number. And so inverting that is not quite as clear. And in fact, this will play a role in the theory, right? That functions will have many branches, and this will be a key point. So I just wanted to give this example because it's sort of the simplest one where this arises. Okay, so now, I mean, you can read in the reference about how the complex numbers are sort of the natural object in the sense that they are a field. They have very nice algebraic properties. Any other way that you would define them to satisfy these properties, it would be bound to essentially be the same as this. But I will not go into this. You can read it in the reference. But you can maybe one good thing to keep in mind. Yeah, maybe this is a point worth making, is that if, when I take x squared plus 1 equals 0, right, there are two solutions, right? There's I and minus I. It's not clear at all how, right, what is I and what is minus I, right? I could have defined I as being minus I and I am, right? It's not even quite clear how to make sense of this, but I could have made the theory, I can pick one of the roots of this polynomial, but I can also pick the other root. Right, and so in particular, if I replace all i's by minus I, sort of everything should still be the same. Right? And in fact, this is the case, and it's a good exercise to try and see this, but this also motivates a transformation. Right, and this transformation is the idea of a conjugate. Right? And it's just where you transform I to minus I. So if I have a number A plus I, let me use alpha plus I beta, right? If I take its conjugate, which we write this way, then the conjugate of this is just alpha minus. Right, and this will be a very important operation. Right, so oftentimes we'll write, I've just written real numbers, but I can write things like, right, I usually use letters, say like A to be, right, to be this complex number, and now this is a complex number. So, right, so now the conjugate will just be alpha minus I beta. Okay, now things to check. Okay, so I recommend you just check this, check this at home. That if I take two complex numbers, right, so I'm going to use Latin letters for complex numbers and Greek letters for reals. At least for now, I'm not sure how consistent I'll be, but from context will be clear what kind of numbers it is. Right, that if I take the conjugate of the sum, this is just the sum of the conjugates. This is kind of obvious, right? Because I think it's pretty obvious, but to work it out. Maybe a lot less obvious is what happens to the conjugate of the product. Right? And so work this out and see what happens. Maybe one way to view what, to not be as surprising that the conjugate of the product will just be the product of the conjugates is that indeed if you replace I with minus I, everything should go through, right? Because minus I squared is still minus 1. It's just that all i's will be replaced by minus i's. Right? So then if you think about it that way, it's kind of clear that this should be the case. Okay, and we're out of time. Let me just write something else for you to think about, which is trying to show that number A times the number times conjugate times its conjugate is bigger or equal than 0. Okay, so and show Okay, what is A times A conjugate? Okay, and so we're now out of time.